Hi, this video is a part of Deep Learning with TensorFlow playlist. In this playlist, I quickly explain the logic and implementation of deep learning algorithms and applications using TensorFlow. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and re-implement them yourself. Code files for each video will be given in its description. So I'm expecting my audience to be well versed with deep learning understanding and TensorFlow understanding, and they just need little hints for implementation of deep learning algorithms using TensorFlow. In this video, I'll talk about text classification with word embeddings. Text is special because we have to convert it to numbers, tokenize it, capture the meaning of words in it. That is, we have to do word embeddings. We have to learn the word embeddings or load the pre-trained word embeddings. Moreover, the sequences like structure demands one-dimensional convolutions or recurrence of neural networks. And then there are a lot of technical details to deal with this text kind of a structure where we have uneven length of sentences. So how do we pad different sentences, and how do we deal with words which are not in our vocabulary? So there are a lot of details dealing with text. Let's jump to the whiteboard and notebook to understand the idea in better way and code it in Python. Okay, so the first thing that we have to do is basically tokenizing the words to unique numbers. So consider we have corpus of data, so all of the text that we will be dealing with in our training data set for text classification is what we call corpus. So all of the words in our corpus should have a unique identity, should have a unique number. This process is called tokenization, and TensorFlow has great functions for tokenizing those words automatically. However, it is really easy if you want to do it manually. We have to just create a dictionary, and in Python, the dictionary can do this work, where we have to map the value, the key value. Where we have to find the key value pair. So for each of the unique word, we have to have this unique integer number. Now, after tokenization, this is the first important thing that we have to deal with. We have to do while working with language. Each of the word must have a unique number. Then secondly, the second most important part is that the number that we are giving to the word does not contain any meaning. So we cannot use those tokenized numbers directly. Consider we have a sentence that the poor man has no money. Now, this whole sentence makes sense, but the individual word, if it is mapped to a single number, integer number, randomly to 50, money to 50, man to 45, poor to 1005. So all of these numbers individually does not make any sense. They do not capture the meaning of this word money, or this man, or this poor. So how do we capture the meaning? This is done by word embeddings. Word embeddings is a great idea, and there are a lot of unsupervised learning algorithms. For example, glove is one of them, which is what we call global vectors. Global word vector representation. So you can find out the details about it, and it is an unsupervised learning algorithm where we find out the co-occurrence of different words, and based on that we learn different vectors for each of the word. The vector contains the meaning of the word. So for example, we have a 16-dimensional vector that we have learned through some unsupervised learning algorithm. That could be glove, that could be our own way of learning, while not in unsupervised manner, rather while doing this classification task, we could also learn this word embeddings by first initializing, consider we have 1000 vocabulary words, and for each word we are having 16 dimension vector. So we will initialize this 1000,16 matrix. This is what we call word embedding matrix that we will be initializing in the first layer, and then using this matrix, this will go in the next layers, and finally we will be having this output prediction task, and based on that we will adjust the weights of all the layers, and of course this embedding matrix layer. So in adjustment, what will happen is that these values, these weights inside this matrix will adjust accordingly in such a way that finally, after successful training, this whole matrix will learn and capture the meaning of different words. For example, but this is only possible when we have lots and lots of data. So lots and lots of data is necessary for this process to happen. However, and it needs a lot of computational power, but we do not have that. But still, we will be looking at training those embedding matrices, this embedding matrix from this classification task. And we will also look at the pre-trained glove vector representation, and we'll be loading this pre-trained glove vector stored in the text form that I'll be explaining. Just let me show you that this is how it looks. Consider this word the. This is the word the, and this is the word and this is the word said. So there are a lot of words, for each of the word we have these different numbers. The first line contains the vector numbers. There are different vector numbers. I guess these are 100 numbers, 100 dimension vector for this word the, which contains this meaning of the. So, and it has been learned using different statistical rules, which is explained in this glove algorithm, and I'm expecting that you know about it, and you must search about it in detail. However, the main idea is that we need to capture the meaning of words in such a way that we have numbers, vectors, and these vectors should be similar for similar kind of words. Consider this good having this vector, and inside this vector we have numbers 5, 10, minus 90, and for excellent it should be close to those numbers 6, 8.9 and minus 88.9. So in a way, if we were having two-dimensional vector, so this should be, if it is great, if this is the vector for great, then the vector for excellent should be close enough. So this is the main idea, that in vector space we want similar word to exist together in vector space. And how is it possible? By learning the representation, by learning these vectors in unsupervised way or supervised way. But this task is usually done in pre-trained manner, and this task could also be done by capturing the meaning of sentences instead of words. So this is a whole subject, and you can find out the details about it. However, the main idea is to capture the meaning of the words instead of just having these unique numbers. This unique number is also important, but we also need, during training we will be needing this representation of words in such a way that we capture the meaning, and this is done through word embeddings. The third part is basically, in text we have to deal with this fixed length input. Consider a sentence which is having a total 8 words, and another sentence which is having total of 12 words, and another sentence which is having total of 30 words. So there are different length of sentences. So these sentences of different lengths cannot be used directly for training, because neural network is expecting a same length for an input. So what we'll be doing is we'll be defining a fixed length input, consider 15, and this first sentence will be padded with extra word, which will say that these are extra words, which will be a unique ID for the extra word. These are padded words, so that the length becomes 15, and it will be padded for 3 more words. 3 more padded words will be added to make this length 15, and this will be truncated. This 30, the sentence of having 30 words will be truncated to have this first 15 words. This padding and truncation could be done at the start of a sentence or the end of a sentence. Both of these are possible, but we'll be doing at post padding, or the end of the, we'll be padding the end of sentence and we'll be truncating the end of sentence. So once we have that, then the fourth thing that we'll be dealing with is the words out of vocabulary. So consider we have learned the word embeddings for English vocabulary containing 50,000 words. However, it is possible that our input data is having sentence, and that sentence is having words which are not inside these 50,000 words. So for that, what we'll do is we will call that word an out of vocabulary word, and we will assign a special token for that, assign a special number for that. So we'll represent all of those words with this special token, that we do not have this dictionary, we do not have that word in our vocabulary. Okay, then finally the fifth thing that we will be dealing with is the unimportant words in sentences. If we look at the sentence, usually there are a lot of punctuations and there are a lot of words that do not capture the meaning, and those words are basically nice. We can understand those words, but when we perceive the meaning of sentence, those words do not make any significant impact in understanding of their meaning, their internal meaning, their main aim. So the sentence meaning is captured by most important words, and there are a lot of words which creates noise. So we will be also removing these unimportant words and these punctuations. This is what we call cleaning the text. So we clean the text for further processing. So these are 4 to 5 steps that we will be dealing, that we should be aware of when dealing with text. Now we will be working with all of these 5 steps in the notebook, but before that, let me just tell you one more detail about text. So this is what I have already explained, this vocabulary thing. Consider we have 1000 words in the vocabulary and 16 dimension for each of the words. So word embedding will be having a matrix of shape 16,000 comma 10,000 comma 16. Now the final detail is that we are dealing with text, and text is a sequence. By sequence, what we mean is that each of the word is actually dependent upon the previous word. As look at this sentence. In this sentence, this money contains no meaning individually, but when it is seen as a whole, it contains this meaning: no money, totally negates the meaning of only money. If I say the poor man has money, so it is a totally different sentence, but saying that the poor man has no money just totally changes the meaning of a sentence. So in a way, we have this structure where the structure where the word is dependent upon the previous words. So in a way where we were having images in 2-dimensional or 3-dimensional, where each pixel was affected by surrounding pixels, so for that reason we used convolutions, 2D convolutions or 3D convolutions. So in case of text, we will be working with 1-dimensional convolutions. And we'll also be working with this recurrence structure in neural network, where each of the where there will be recurrence, where the output of each of the word will be used as an input for the next word prediction. So this is captured in GRUs and LSTMs, and I'm expecting that you know the details. For TensorFlow implementation, this GRU, this LSTM, this con 2D or 3D or con 1D, they all are same almost. They are implemented using single function. However, of course, the parameters for a function for each of this different layer, this GRU layer, LSTM, con 1D, 2D, 3D will be different. So the parameters will be different, but the implementation is same. So if you know if you have this broad understanding of LSTMs and GRUs, you are still good to go. But it's good to understand the technical details of LSTMs and GRUs. This series is basically application series using TensorFlow, so I won't go into the details of how this works. But I'm expecting that you know about it. Let's jump to the notebook to understand this whole idea in more detail and code it in Python. We begin by importing all the necessary libraries. Then the first part is that we also want to train the word embeddings. Of course, this will not be the real word embeddings that we'll be using, but still the process is same. So if you have this computational power and lots of data, then you could do it extensively. Here we are using only vocabulary of 1000 words, and the embedding dimension is only 16, and so the matrix will be 1000 comma 16, and we are using the maximum length of sentence to be 120. So if it is not 120 or greater than 120, then we will truncate it. In case of less than 120, we will pad it, and the padding and truncation will be done in post manner, so it will be done at the end of sentence. And we are just initializing and declaring this token for out of vocabulary. So this is the out of vocabulary token that we'll be using for each of the word which is not inside the vocabulary. Okay, then we have this training portion where we are using 80% of the data for training. Now these are some of the stop words that we won't be using, because they do not they are not important, and they do not capture the meaning and gist of a sentence. So for that reason, we will not be looking at those stop words. That's why we'll be replacing those words with this empty string. One thing. Secondly, this is just opening the dataset that we are having in comma separated file, and we'll be using that comma separated file for removing those stop words and then appending the sentences, separating the sentences and labels for each of the sentence. Okay, given these sentences, this is the whole sentence: TV, future, hands, viewer, home, theater, systems, plasma. Why does it not make sense for us at this point in time? Because we have replaced these stop words. These stop words have replacing and removing these stop words are actually making it kind of difficult for us to understand. However, the meaning is still captured inside this sentences. The most important words are still there, and they will be used for classification task. Next, what we'll be doing is splitting the dataset into training and validation. And once we have done that, then we'll be tokenizing the sentences. Each of the word, once tokenized, will have this kind of a structure where we are having this token, and for each of the token, or for each of the word, we are having this integer number. There is a word S, for that we have the integer value of 2. Then said, it is having integer value of 3. Each of the word in our vocabulary will be having a unique number. So once we have tokenized that, then let's look at some of the words and some of the sentences. So this is the sentence, and for each of the sentence, what we are having is this tokenized numbers, integer numbers. So each of the word is actually replaced by its tokenized number. Okay, once we have done that, then what we'll do is we'll also tokenize this validation sequence, and this is how it looks. And after tokenizing sequences and sentences, then we tokenize the labels, the output, and we are having 1-dimension label, and there are total 6 different labels. So this is a multi-class classification problem. Then we define our model in sequential manner, where our first layer will be embedding layer. This embedding layer is what I was talking about, and it will be having a dimension of vocabulary size comma embedding dimension. In this case, it is actually 1000 comma 16. Next, we will be having this input length of maximum length. The input length is actually 120. So each of the sentence will be having a length of 120. Then given this input sentence, this input sentence having 120 different words, each word will be having this dimension of 16. That is what is represented here. So each of the word is having a dimension of 16. Now then what we will be doing is that we will do global average pooling. This is again a one-dimensional pooling, and once we have this one-dimensional pooling, we get this single dimensional vector of 16, and then we apply this dense layer of 24 neurons or hidden units, and then apply this final dense layer of 6 units where we apply this activation of softmax. This is the final layer, and this will output the probability for each of the class. So we compile it, and we are using this loss sparse categorical cross entropy because we are dealing with this multi-class classification, and we are using this Adam optimizer, and we'll be looking at accuracy and looking at this fitting function. We have training data, we have validation data, and we have 30 total number of epochs for which we want to train it. And once we train it, these are the graphs that we have received. Okay, this first part is really easy, but once we have learned the word embeddings, then we want to visualize the word embeddings, as I've already explained that the vectors of good and excellent should be placed close together. But how do we visualize this 16-dimensional vector? For that, TensorFlow has its own embedding projector, and we could use that embedding projector to visualize these results. But how do we do that? For that, what we'll do is, first of all, we will open these two files, vec.tsv and meta.tsv. So the extension will be .tsv. Now then what we will do is that we are having 1000 vocabulary size. So the total words are 1000 in our vocabulary. For each of the word, what we will do is, so this is word number, so the integer value will be from 1 to 1000. Then what we will do is this word number will be having value of 1. So given this reverse word index dictionary, the key value of 1, what we'll extract out is this word. Why? Because this is explained here. So reverse word index is here a dictionary, and this dictionary is basically reversed, and this dictionary is a reverse form of this word index, and word index contains the tokenized numbers. So the tokenization number, the tokenized values having word and its associated integer value is stored in this word index. But this reverse word index is an opposite dictionary containing a key value of integer, and for each integer key value we have the value of word. So given this word number, we extract out the word. So for integer 1 we have a different word, for integer 2 we have a different word, and for integer 3, 4, 5 up to 1000 we are mapping this single integer, each and every single integer, to a unique word. And given that word, what we will do is we will extract the weight for that word, and we'll store it in embeddings, and then we will write the word in meta.tsv, and we'll write the embeddings in out_v, so like vex.tsv. And then once we do that, then we will use this TensorFlow embedding projector, and we'll load these two files, vex.tsv and meta.tsv, and you'll be able to visualize these two vectors. Okay, now I'll show you these two vectors at the end of this notebook, but let's begin looking at the pre-trained word embeddings. Now consider another setting where we do not have to train the word embeddings, and we are loading this glove vector representation. So all of the other things are completely almost same, except for these sizes where we are having 100 embedding dimensions instead of 16, and we are having maximum length of sentence to be 16, not 120, and we are having this training size and training portion to be 0.1. Otherwise this loading of data is same, and then we are having this padding and tokenization. All of these things are same except for this single matrix, except for this single cell where we are loading this embedding index. How do we do that? We open this text file, and this is the text file, and in this text file the first word is the first entity is basically the word, and all of the other entities in this line is a vector for this word. So this is what we will be doing. So for each line we are having this first value to be word, and all of the other words to be its coefficient are the embedding vector. And once we store it in this dictionary embedding index, then what we will do is we will, for each of the word in our tokenized words in our corpus, we will extract out that embedding vector for the word in our corpus. And once we have that, then we are having total words of more than 138,000 words in our corpus, and there are for each word we are having 100 dimensions. So these are pre-trained words pre-trained word embeddings that we'll be using. And how do we do that? Then we will again use this embedding layer as a first layer, where we are defining the architecture of our model. However, the difference is that we will be giving this trainable option to be false, because we don't want to train it. It has already been trained, so this layer won't be trained while we fit this model. So next what we'll do is we'll apply this dropout. Then this is 1D convolution, then this is 1D pooling, and this is LSTM application, and this is again final dense layer, where we are just applying this where we are just predicting the single class. So that's why we are using this binary cross entropy and not categorical cross entropy. And again, this is the summary, and given the summary, we train it for 50 epochs, and using that we have the results. These are just plotting the results. Okay, I hope so this makes sense. Let me show you the vectors in projector. Okay, so this is basically a word to vec 10k words, and we have these embeddings of 200 dimensions, and this is basically a t-SNE algorithm, t-distributed stochastic neighbor embeddings. In a way, we have done it to just visualize the words. So consider we are looking at this word, and this word is infectious, and close to these words are disease, and all of diagnosed complications, and all of the medical words, the depression, the immune and acute, and drugs and alcoholism, all of them are close together. And this is the main idea of word embeddings. And if you look at other words like sex, sexuality, and this is the circumcision, masturbation, and all of these words are really close together, and they are close, and they have similar kind of a meaning. So these are different names, Kelly, Doc, Murphy, Parker, Mitchell, they are close together. And at this end, what we have is first, final, and once, after, during, quickly, gradually, finally, slowly, decayed. All of these words do occur together, and they have similar kind of meanings. So that is what we mean when we talk about a word embedding.